Everybody's favorite story of what's happening in quantum mechanics is really ugly from somebody else's point of view. We have this fantastic machinery of quantum mechanics and we can build all these technologies with it, but we have a problem with the philosophy of quantum mechanics. And this is very similar with probability, actually. The philosophy of probability is a mess. The start point of QBism is the question, what are probabilities? Chris Fuchs says we should really think about quantum mechanics as our best guide to shape our probabilities. These things are not parts of the world. QBism is extremely useful. It helped me understand a lot of physics, a lot of the counterintuitive aspects of quantum mechanics. But then I started actually doing research, and my supervisor, Carlo Rovelli, he's the main proponent of relational quantum mechanics. We had a very long email discussion. It was during the pandemic, so we were stuck at home. He was to reignite an instinct within me, which is the instinct of trying to understand the world. One of the things that QBism doesn't really allow you to do is say something like, what is happening on Mars? And in relational quantum mechanics, the state is relative to another system. It's a collection of all the relationships that one system has towards the other. Wigner is sitting outside the lab and he's just thinking about what his friend is saying. Is there any sense in which the stuff that's happening to Wigner and the stuff that's happening to friend, while they're not interacting, live in the same reality somehow?
What account does relational quantum mechanics give of what's happening here?
And there were a few things that made me not consider Everettian quantum mechanics very seriously. The mathematics predicts that inside the box now there are two patterns. The pattern of the friend sees outcome 0 and the pattern of the friend sees outcome 1. People embedded in the multiverse somehow can use the probabilities of quantum mechanics to guide their decisions. I think it's still very counterintuitive. It hasn't really solved the problem, I would say.
Hello, welcome back to the Quantum Foundations podcast. I'm Maria Villaris. I'm just finishing my PhD in quantum information at the University of Oxford. Today I'm in Vienna and I'm joined by Andrea Di Biagio, who is a postdoc here at IQOQI Vienna. Thanks, Andrea, for joining us today.
Yeah, thanks for having me.
So today we're going to talk about Andrea's journey through different interpretations of quantum mechanics, where he's done research on different aspects of these interpretations. So I hope you enjoy. And the idea of this installment of the podcast is that we aim to make it accessible to anyone who's interested in the topic. And please leave any questions or comments you have in the comments of the video and I'll try and take a look at them. So yeah, thanks for joining us. So Andrea, could you tell us a bit about how you ended up doing research in fundamental aspects of quantum physics?
Yeah, sure. So it was a bit of a torturous journey because I started physics as you do, as a university, and I wasn't quite sure if I was cut for doing research, but in the end I ended up doing it. And I guess when I was finishing high school, I was looking at all the possible subjects I could do university in, like I could do my studies in. And sort of the thing that tipped the scales from material science, engineering, and all these things was one night I was reading the Wikipedia article about the double slit experiment, which is this fundamental conundrum in physics that I guess we'll talk about more. And I was just amazed that such a simple thing was not understood. Well, firstly, I didn't understand the mathematics on the Wikipedia page. There were all this notation that I'd never seen, this bracket notation. And I thought that was weird. But mostly I realized that people were really debating this issue still, I don't know, maybe 100 years after discovering the effect. And I just thought I couldn't be right. So then I decided I was gonna try to figure it out. And of course, between that moment and actually finishing my master's degrees and actually committing to doing a PhD, that was a long, long journey, but somehow the thing that brought me to physics was this deep mystery. And the fact is, we are still all very confused about the double slit experiment. So, and me too, including me. So I don't know how that's going, but it's really fun to do research in these things.
Cool. So yeah, maybe a good place to start to set the scene is to explain the double slit experiment and what the issue with it is. So could you just give us a summary of what it is and why it's weird?
Right. Could I maybe just make a tiny diagram here?
Yeah.
Yeah. So we have here it is an actual working blackboard. This one is not just for show. So the double slit experiment is simple, really simple thing. I'm making a picture like, say from above. You just have a screen, like a piece of metal or something, with two tiny holes, this and this. Of course, you cannot see really well, but you can see actually. But
I think it's fine.
Yeah, this is just a wall. The slits are actually minuscule, but here, for dramatic effect, they're big. And you have a thing over here that is like either a laser or some radioactive material that can shoot particles. If you just let it be, it will like shoot particles. And if you put some screen here, you can see that that stuff arrives to it like dot by dot. Sometimes things fly through this space, okay? But you put the screen behind the slits. Okay, so here, say that we only had one slit for the moment. You closed one of them like this, and you let this thing sit here. You'll get like a dot here, and then a dot here, and a dot here, and a dot here, and you just wait for a while. You accumulate number of dots that arrive. These are particles that are arriving on the screen, and what you get is something like, if I draw the number of slits, number of detections per little piece of the screen, then you will have something like, there's going to be like many particles hitting right behind the slit, right? That makes sense. Like things are flying through and they hit like right behind this thing. If you open this slit and you leave this one closed, then over here what you get is very similar. You just get many particles hitting right behind the slit and not much anywhere else. Okay, so far so good, nothing is weird, but it's called the double slit experiment because what happens is that if you now have both open and you let the particles hit the screen, you just wait for a while, you might guess that what you get is something like before, like you get the two shadows of those two slits, let's say. But in reality, what you get something completely different, which is actually what we call an interference pattern, which I'm gonna try to make my best because I'm not an artist, but it's something like this. So all of a sudden, the pattern is completely different. I mean, all of a sudden, you have to wait for the statistics, for the particles to arrive. But now that the two slits are open, you don't get the sum of the two patterns. You get a new thing where you have many particles arriving where before none was arriving, because before most of them were concentrated here and here. So now you have a lot of particles where before you didn't have some, and in the place where you had a lot of them, now you have very few of them. And somehow, what's important to understand here is that they're not all flying through this space and bumping onto each other and doing something like that. This happens even if you send literally one particle at a time. You just wait for them to arrive. And so somehow you have this thing flying through space that when it arrives on the screen is a dot, but then somehow it also knows that both slits are open, so it cannot be going only through one, because somehow the fact that this one is open matters to where the particle will arrive. So it's going through both of them, but then how can it go through both of them? And these are kind of the questions people ask themselves, and endless debates about it. This Richard Feynman, who, if you ever start doing physics, you certainly know. Richard Feynman said that this is the central mystery of quantum mechanics in a way. And I mean, modern researchers maybe would say there's other things that are more central to quantum mechanics, but this is pretty close to why quantum mechanics is counterintuitive. And obviously it's not just this thing, it happens in many different situations, right? Like it's important to many phenomena. And the interpretations of quantum mechanics is sort of like finding ways to make sense of this kind of behavior.
Yeah, great. So when we were talking recently, you said that at first you liked the QBist interpretation of quantum mechanics. So could you tell us a bit about how you ended up liking the QBist interpretation and what it actually is, how it explains quantum mechanics?
Right. So, if I may, just before getting to that, I would like to say that when you study physics, in most departments, they just teach you the mathematics, the physics itself. You study the energy levels of the atoms. You study particle physics, field theory, and all these things. And we have this mathematical machinery of quantum mechanics, and we are extremely good at applying it. Like as a community, as a species, we use quantum mechanics all the time, but we don't teach necessarily the philosophical questions.
Yeah.
And so it took me a long time to you get exposed to it, especially if you're curious, you read books and you kind of see the different perspectives. But the problem is very complex, and so it takes a long time before you actually start understanding what people are talking about.
Yeah.
Okay. So that's kind of a little preface. And QBism is one of the, I think, is fairly recent interpretation of quantum mechanics, and the main representative of QBism is Chris Fuchs, who's long-standing researcher, made many contributions, technical contributions to quantum mechanics. But I would say most likely he's going to be remembered for his work on the conceptual foundations of quantum mechanics. And I got into his work when I started my PhD. As a procrastination method, I got to do a couple of courses in plasma physics and things like that to get the credits. But I like to read research when I don't want to work. It's a fantastic method to feel productive while procrastinating.
Yeah.
And I started reading his stuff, and I just read like 10 of his articles in a row, and it really kind of shaped my understanding of quantum mechanics. The main thing, so the start point of QBism is the question, what are probabilities? And if you want, I can get into that for a bit. Yeah, sure.
Yeah.
Okay. So okay, this is, and it's funny. I like to make this parallel all the time. I just said that that we have this fantastic machinery of quantum mechanics, and we can build all these technologies with it, and we can study, the beginning of the universe and all this stuff. But we have a problem with the philosophy of quantum mechanics, and this is very similar with probability, actually. So we have this fantastical mathematics of probability. It's called Kolmogorov axioms of probability and stuff like that. And anyway, we learn in school how to apply it. I did it in high school. I think most people do it too. And we have statistics. We study. We can answer questions like, what is the probability of drawing three hearts in a row from a deck of cards? And these are things we can answer very easily. Everybody agrees. We use it all the time for engineering, spaceships, medical decisions of medical policy and stuff like that. But the philosophy of probability is a mess. I mean, it's not as bad as quantum mechanics, I would say, because there's more philosophers, so they actually, they're good at doing philosophy. We have a lot of physicists that start doing philosophy before any training.
Right.
So that can be a bit messy, but still, it's still a disputed subject. And that's where Chris Fuchs starts with his interpretation of quantum mechanics. Is like, quantum mechanics, one of the main things that quantum mechanics gives you is the probabilities of things happening. So here I showed you this pattern, right? And this is like accumulation of many events, things that like something leaves from here and lands somewhere here. And quantum mechanics allows you to compute this pattern, in the sense it gives you the probability of where the particle will land, right? So we have a theory that gives you probabilities, but fundamentally we don't know what probabilities are. And Chris Fuchs has this idea. Well, it's not his idea, but one of the main ways of understanding probability is somehow as a degree of belief. So if I tell you, what are the chances it's going to rain tonight, you're gonna say, I think 80%, but that means that you're pretty confident it's going to rain tonight. It doesn't actually mean that it is going to rain tonight. It might not mean anything about it. Might have no relation to the actual state of the world. It's just your belief that it's going to rain.
Right.
Somehow, it's a kind of a way to measure belief, probability.
Yeah, so it's a property of me, not a property of the actual weather.
Right. And of you and of me, everybody has their own probabilities, and they're called subjective probabilities. And Chris Fuchs says we should really think about quantum mechanics as our best guide to shape our probabilities, our subjective probabilities. So given what I know, given what I believe about how my experiment is set up, quantum mechanics tells me what other things I should believe are going to happen. How should I decide?
Right.
And he makes this concrete in terms of bets. So if you say there's like 80% odds for something to happen, it means that you are willing to buy for 80 cents a ticket that is worth $1 if the thing happens. And if you start with that, and you start with some arguments of like, what are the ways that I need to organize my beliefs so that I cannot get fooled, you get all of probability theory from this. This is a thing that was known for a while.
Right. Yeah. Yeah. So the idea is that quantum mechanics is telling us how to assign these beliefs given a certain situation where we're going to apply quantum mechanics.
Right. Right. And in particular, maybe you guys, you people have heard already stuff about like virtual particles and fields and atoms, cloud of atoms around the nucleus and all these things. Quantum QBism says these things are not parts of the world; they're just things that we see when we do our computations to compute the probabilities, but we should not assign like necessarily reality to them.
Right.
They are really like features of our mathematics, and we don't know if these things are actually happening or not.
Right. So in terms of what it says about what is actually happening, is it saying that that's something we kind of don't know yet from quantum mechanics? Or is it something we fundamentally can't know? Or is it still a kind of open research question?
Yeah. So we were at a conference this week together, and Chris Fulks gave a talk about this, and also I had a chance to talk to him in the evening.
Yeah.
And yes, so his point is that quantum mechanics should be seen as a really minimal theory, just an addition to our way that we make reasoning, that we make decisions, and as a theory of the world, it should not be taken too seriously. And the main thing that it teaches us about the world is that we should modify our rules of thought a little bit. And this is the most concrete, solid contribution to our understanding of the world.
Modify our rules of thought.
Yeah, in the sense that here, if I have two slits, normally I think, what's going to happen here is something like either the particle goes over here and it gives me this pattern, or it goes over here and gives me this pattern. And I will just, if I use my normal rules of thought, I just imagine, I would have two bumps, two shadows behind here. But actually, no, quantum mechanics tells you that there are situations in which you have to change the way you combine possibilities, basically. And this modification is the fact that this modification leads you to make better decisions is the most concrete thing that quantum mechanics has to tell us about the world. Right. It's very minimal. I think he himself calls it a minimal interpretation.
Yeah, so it's kind of saying, quantum mechanics only tells us this much about reality. Yes. Nothing more than that.
It doesn't want to say that there isn't anything more to understand about reality, but it's not quantum mechanics that's going to tell us that. It's like the same way with probability theory doesn't tell us what's out there. Quantum mechanics also doesn't tell us what's out there. It's just a way of thinking.
Right. Yeah. And do you think with that kind of philosophy, you then does it come with the idea that something else will tell us what's out there, something we've not discovered yet, or something? Is that the kind of idea that?
Yeah, I think it's possible. That I think that's part of what he was saying the other day. If you don't get confused believing that certain things are real but they are not, and you understand quantum mechanics at its fullest, then perhaps that will open a door for the next theory. Instead of filling the world with things that are not there and believing that they're there. I don't know, in the past, some people thought that angels were pushing the sun around the earth, and they were actually pushing it, whereas now we know it's a completely different story and there are no angels involved. And it's not about pushing, but it's about actually pulling towards us. And
Yeah. Right, cool.
Yeah.
And then I believe at some point you shifted from that being your preferred interpretation to relational quantum mechanics. Can you tell us a bit about that shift and then what relational quantum mechanics is all about?
Sure. So once I started seeing physics from a QBist perspective, it was actually very useful in the sense that you start, especially when you work in quantum information theory, which is the study of how information can be processed using quantum systems, where you really work in a very abstract space of ones and zeros and stuff like this. You don't really think about atoms and fields and actual physical objects. You think about abstractly. QBism is extremely useful from that point of view, and it helped me understand a lot of physics. A lot of the counterintuitive aspects of quantum mechanics are a bit more natural if you think of quantum mechanics as thinking, somehow propagation of knowledge. But then I started actually doing research, and my supervisor, Carlo Rovelli, he's the main proponent of a different interpretation called Relational Quantum Mechanics. And when I started talking to him about, I don't remember exactly what topic it was, probably Wigner's friend, which we might get to later. We had a very long email discussion. It was during the pandemic, so we were stuck at home, and we were sending each other like 2 emails a day, like super long emails, and we had a really intense discussion, and it's just the beginning of an unending thread of very intense discussions over email. And it's fun, it's good fun. But basically what he did then, he was to reignite an instinct within me, which is the instinct of trying to understand the world as it is, using our best theories of physics to see what is actually out there.
Right.
So it's one of the things that QBism doesn't really allow you to do is say something like, what is happening on Mars? Because QBism is about how you update your own state of belief about what's going to happen next to you as a person. So there's also this special role of people in this interpretation.
Right.
And so you couldn't really answer the question, what's happening on Mars right now? Because if there's nobody on Mars, and what that means in the QBist perspective, it means that if I believe something is happening on Mars, what I actually believe is that if I were to go and find a thing that allows me to check that something is happening, what is happening on Mars, I might guess something. I can open NASA's website and go and see where Curiosity rover is, or where the Chinese rover is. And it's not about what's actually, there's no sense in which something is actually happening on Mars. It's more about what is going to happen to me when I check.
Right. So it's always about you.
Yeah.
In some way.
Yes.
It's always related to you.
Yes, because quantum mechanics is about shaping your beliefs, and quantum mechanics can be used to understand beliefs about what's going to happen next to you. Maybe I should have said that earlier. But yeah, it's about your subjective experience somehow. And I felt, after a bit talking to Carlo, I realized how constrictive that feels in a way. Like, why should I limit myself to thinking just about me? And also, there are different currents in philosophy of physics, but one of them is naturalism, where you want to understand the world independent of human observation, let's say, where humans they don't play a fundamentally special role in the theories necessarily. They play a special role, of course, because we are the only system we know of that goes around and does experiments and understands how things work and care and build bridges and all these things. But they're not at the beginning of the theory, as one of the elements that are. We also have to be described, understood. We're not part of the theory that cannot be analyzed. Is naturalism, I would say.
Yeah.
And that's also the reason why many people start doing physics, is because they want to understand how the world is. And then they realize the world is a mess. And so it's easy to take a step back and let's think about, not the world as it is, but the relationship between the world and me. And QBism is kind of the end product of this, this shift.
Right. Cool. So how does relational quantum mechanics explain what's happening? And if it's useful, we could use Wigner's friend as an example, or some other example.
So relational quantum mechanics in the end is not that different from QBism. in the sense that it's still about, so probabilities are, so still quantum mechanics is the best tool to compute what's going to happen next. You know, I guess your audience has heard about the wave function, maybe.
Probably.
But anyway, there is this discussion. One of the big questions in quantum mechanics is the wave function real? And stuff like this. Is it part of the world? Is it part of the mathematics only? And also in relational quantum mechanics, like in QBism, the wave function, so-called the state vector, or the state, is mostly just a part of the mathematics.
And if anyone doesn't know, the wave function refers to this quantum state describing the whole universe, if you apply quantum mechanics across the universe.
Yeah.
Yeah.
But in most applications, the state applies. You have a system. Often it's a piece of metal or a semiconductor or like some like optics experiment in your lab, or you're considering maybe a single atom. Often the state is assigned to a system of the universe, not the whole universe. But yeah, in principle, there are interpretations where you have the state of the whole universe. But in relational quantum mechanics and in QBism, the state is always assigned to a part of the world, and it's relative to another part of the world. And in QBism, it's relative to you. So the state is kind of cataloging your beliefs.
Right.
And in relational quantum mechanics, the state is relative to another system, and it catalogs it, like it's a collection of all the relationships that one system has towards the other. So,
right. Yeah, so it kind of removes the observer specialness from QBism and shifts to more subsystem relative.
Right, exactly.
So it's kind of more symmetric in a way, that it's not revolving around an observer and their beliefs as like everything in relation to each other has this. Yeah, that's right.
So it's more, so in a way it's democratizing what systems can be the observers in a way. So it's like in QBism, people, agents, or even maybe AIs, but agents with beliefs, and they can take action. Those people can be the observers that can use quantum mechanics to predict the future. Whereas in relational quantum mechanics, the idea is that all systems have relations to all other systems, and quantum mechanics can be used to understand this relation with respect to any system, not just people. So maybe we should take a second to say that in quantum mechanics, the way you get it in textbooks, there are all these words like measurement and observer, observation, that are not, that's what we are debating about. Like what is an observer? Like what is a measurement? And stuff like that. And many interpretations, they differ from each other because they answer this question differently. And yeah, in the case of QBism, the observer is a person, or like maybe a robot, AI, something. And in relational quantum mechanics, in principle, anything could be an observer. It doesn't have to be thinking or believing anything. It could be the moon, could be an observer in this case. It just needs enough structure to actually be affected by things.
Right. Yeah. And relational quantum mechanics can tell us what's happening on Mars without involving us in the story, because we can talk about Mars as its own subsystem interacting with other subsystems, none of which involve us personally. Right.
Yeah. You can have situations where you can just say, okay, what's happening to this system? And in that sense, is like the relation that that system has towards the rest of the world is, stuff happens to it sometimes. And you can model that in quantum mechanics in principle.
Right. So it might be interesting to kind of summarize the Wigner's friend thought experiment and then how relational quantum mechanics explains it. Since, you said that was kind of one of the thought experiments that triggered you to be thinking about this more.
Yeah. Right. This is going to be quite a deep dive then, I guess.
We can keep it kind of high level.
Yeah, high level.
Yeah.
So,
do you want to use the board again?
I think I'm going to use the board.
Yeah.
I'm going to see my artist skills again.
Yeah.
So Wigner was a real person. Wigner was an amazing physicist, mathematician. He left a lot of contributions to the technical aspects of quantum mechanics, but the way I interface with this work mostly is through this thought experiment. It's called a thought experiment because nobody has done it. But we might be able to do it one day, or maybe not. We don't know. We were talking about it, I think, yesterday, actually, at the conference.
At the conference, it was a big discussion point. Yeah.
Right. So let's try to keep it as simple as possible while keeping all the features in. This is always a skill. Okay. So you have a person, and it's Wigner's friend. That's why it's called. Because Wigner was imagining how to describe how do I think about my friend that is using quantum mechanics, and I'm Wigner. I'm using quantum mechanics to think about what my friend is doing. So this is the friend, and friend is doing an experiment of some form, and it's a quantum experiment, right? And he can get 0 or 1, say, as a result. Classical experiment. This is, there's many things in quantum mechanics that can have only 1 or 2 values. These are called qubits. Many different physical systems of qubits. And what can happen is that you have a qubit in a certain state, so that when you measure it, you really just don't know what's going to happen, and you get either 0 or 1 in this case, let's say. So Wigner does this experiment. Friend does this experiment, and in the meantime, we have Wigner that imagines that Wigner is sitting outside the lab, and he's just thinking about what his friend is saying. And this is quite similar to Schrödinger's cat in a way, in the sense that one way to think about it is that, okay, when friend sees the outcome of the result, then also friend knows that, okay, in the box something happened, I don't know what, but it's, my friend saw either 0 or 1. This is a bit like the particle went either in the first slit or the second slit. And in fact, the point is that if you instead have Wigner, he says, okay, well, there's a box, and inside the box there is an experiment, but my friend and the experiment are also part of the world, they're quantum systems as well. And if instead of just saying, oh, when my friend sees something, there's a measurement happening, I think, oh, I just model my friend the way I would model any other system in quantum mechanics, what I get is that he is not seeing one or the other, but is in this specific state. It's called a superposition, which is, there is like, the state says, well, either friend, so, well, it's not even either, that's the problem. That's the confusing part when language gets a bit complicated, but the point is that, we couldn't think of the particle going through one slit or the other, but somehow through both or through neither. Quantum mechanics tells you that if you treat your friend as a quantum system, what's happening after he measures is that he either saw 0 or 1, but in reality kind of both or neither, and this state called a superposition, which in very advanced mathematics we denote like this: 0 for the result of the thing, and 0 in the mind of friend, and also 1 the outcome of the experiment, and 1 in the mind of friend. This is a very advanced formula called, this is an example of a state, right? And we literally write these things, so it looks simple, but this is it's like a simplification of a very complicated thing, but in practice you can just think of it like this. And so if the friend just saw 0, then it would be in this state. If he saw 1, it would be in this state, but is in this indefinite situation of having seen either or. I think that's not too bad. Okay. So this is the Wigner friend setup. The point is that if Wigner thinks about friend's description of the experiment, then he should think that something definite happened and he either saw 0 or 1. But if he thinks about it from his own perspective, then he assigns this state to the friend. And this is a very different situation where there is no concrete thing that happened. And one of the main challenge of Wigner's friend is to try to think how come two different systems, observers, can describe the world in such a different way. What does it mean about the world? Does friend have a definite experience, or as Wigner originally proposed the experiment, he said that no, if friend cannot be in this state because this would be a state of not having an experience, and my friend always has an experience, so he must be, he must have chosen one of these two things. But other interpretations are like, no, like friend maybe saw something or maybe not, but Wigner's relationship to the whole box thing is described by this state, so there can be different accounts of what's happening.
Right.
Yeah.
So what account does relational quantum mechanics give of what's happening here?
Well, in a way, it's still a research question.
Right.
I discussed this with Carlo 2 weeks ago when I was visiting him, and we talked about it for days and days, and we've been talking about this for years. And you think it's silly, and maybe it is silly, but we really can't get over this thing. And it's not just us. I mean, the Wigner's friend experiment is really like a huge source of discussions and debate and new ideas. Just yesterday, well, not 3 researchers, but 3 papers were assigned the Polar First Award. Just an award for foundational work in quantum physics, and it was about an extension of Wigner's friend scenario where like these intuitions can get quantified somehow. This like clash of intuitions can be really made precise. So it's not just us, I want to say, but also us in particular. We're a bit confused right now. So the thing is, one way to think about this is what I said before. If I describe the word from the point of view of the friend, then something happens, definitely. And your friend sees something and they move on with their life. And if you describe the word from Wigner's perspective, then Wigner should just not worry about what's happening in the box. If he wants to know what happened in the box, he can open the box and see, right? And in that case, he will also see something definite. But until he does that experiment, we should not really worry about it too much. Even though he will want to think that friend saw something, but somehow the outcome, what friend sees, is a relation between friend and the apparatus. And it's nothing to do with Wigner, who has not interacted with anything.
Right. So because Wigner isn't in that relation, then then Wigner can't say whether the friend saw something definite or not, because that's defined by this relation between the friend and apparatus.
Right, yes.
Because they've interacted.
Yes. So
and Wigner's not interacted.
Right, exactly.
Whereas if Wigner interacts, then the relations now apply to Wigner and the friend and the apparatus, and then now Wigner does say that the friend saw something definite.
Right, exactly. So one thing that comes in the forefront in relational quantum mechanics is somehow that the definite reality we experience comes from constant interactions.
Right.
Right. The relation part is like, okay, I'm sitting on the chair is pushing on me. This is a relation we have to each other, and that kind of gives us the fact that there is definitely a chair below me somehow. And obviously, like people are. From the point of view of fundamental physics, people are enormous systems. We're made of, trillions of atoms or whatever, constantly bombarded with light, and there's light flying between me and you, and so that's a constant interaction that we have. Even when you're sitting in the room alone, you're still interacting with the whole world, and somehow this is what gives stability to the world. But you can create scenarios, you can engineer situations where you're really careful that your system doesn't interact with anything. And while it's doing that, that's when the quantum properties show up more. Right. And in this experiment, this is a thought experiment, to make it work the way that we need to see these weird things, where the difference between these two accounts actually matter. You'd have to isolate the lab from the rest of the world. And this is an awesomely complex thing, of course.
And in terms of the problem that's kind of being discussed or debated in terms of accounting this, is that easy to explain?
Yes, so I think this is a problem also for QBism for a certain extent, and other interpretations where we have this notion of relational facts, relative facts. I should say, in QBism you would get very similar account. The main difference is that in relational quantum mechanics, the friend doesn't need to be a person. Right. It could be like anything really, like a
Cat.
just the apparatus on its own, or a cat, or mice, of course, some virus molecule that can be affected by the result of the experiment, and you would have to ask yourself the same question. Not just when a friend is in the box that can have thoughts and things like this, but just a system that can get affected by another system.
Even a single particle? Or,
in the limit.
Yeah.
So this is one thing we are not quite sure. At the beginning we thought maybe we could make sense of it for a single particle, but a single particle doesn't have enough structure to know that anything is happening to it in a way.
So there needs to be some level of structure.
Yeah.
So some kind of threshold.
Yeah. And maybe there's like some sort of gray zone, from and maybe it kind of builds up, but this is an ongoing development.
Okay.
So
yeah, that's interesting. I didn't know that.
Yeah, but the main problem with these kind of explanations is that, and let's just refer to people because it's easier to speak, but it can be also this kind of other more like general systems. But the thing is, okay, there's Wigner, and Wigner has the collection of facts happening, like things happening to him, all the relations he has with systems through interactions, and then there's Friend, who has all his own relations with the rest of the world inside the box. This world is very small in this case, but they're all inside. And one active question is that we're asking ourselves as a community, as a small part of the community, but people that work on these kind of problems, is there any sense in which the stuff that's happening to Wigner and the stuff that's happening to Friend, while they're not interacting, live in the same reality somehow? Like, is there a collection of all the different perspectives of all the different systems, and do these perspectives match up? So when Wigner opens the box, is it meaningful to say that he actually saw what Friend had already seen before he opened the box?
Right.
Is this a correct way of thinking?
Right. Yeah. So before and after these different observers interact. Yeah, is Wigner getting an insight into the world that his friend was experiencing, or is it kind of something on a different level once they've interacted in a way?
Right. Yes. Like does the interaction change things for Friend, or does it reveal what happened inside before Wigner opened the box, or is it something more? Maybe it's something more exotic, like actually from Wigner's perspective, Friend really was not there until he opened the box. And this is a bit scary, and it's not ugly, but there are. It's a bit more complicated than this experiment that we just said. There are other things you can consider doing to the Friend, which are not very nice, but they're like you can just do it. You don't have to actually do it. You just have to think about the possibility of doing it, and somehow the details of it force you to ask questions of the form that I just mentioned, like. Is there really a way to match what Friend sees and what Wigner sees? And of course we want that to be the case because we are living together in the world, and we don't want to have a theory that tells us that what I see is completely unrelated from what you see.
Yeah.
Because in many concrete sense, it just is not the case. Like it's concretely the case that we see the same things. Like we can talk about, we are having this conversation, we agree that we are in Vienna and all these things. So obviously agreement is a fact of the world, and we want a theory that has this. Otherwise, it's a bad theory.
Yeah.
Otherwise, it tells us that we got lost somewhere.
Yeah. Right. Cool. And then more recently, you've shifted more to the Everettian perspective, or many worlds perspective. Or interpretation of quantum mechanics. Could you tell us a bit about that shift and what this many worlds view or Everettian view is, and what your thoughts on that are?
Right, sure. So so recently I've been getting, and by recently I mean the last 3-4 years, I've been learning more and more about we can call it Everettian quantum mechanics.
Let's go with that. Yeah.
I don't like the word many words.
I think lots of people don't. Yeah.
Yeah. It's got a bad rap. It's like it's like saying that you're vegan. Unfortunately, I'm vegan because some people are annoying. But I think it's a egregiously sensible way of looking at things. But it's completely it's very counterintuitive. And this is the problem. I think most people working in this field of interpretations of quantum mechanics, there is this truism that is all interpretations they're unpalatable, they're like they're unpleasant in one way or another. And this is also a way to understand why quantum mechanics is so weird. Everybody's favorite story of what's happening in quantum mechanics is really ugly from somebody else's point of view.
Yeah.
And this is a way to say just how confusing quantum mechanics is.
Yeah.
So all this being said, so when I started, when I got into QBism and relational quantum mechanics, these interpretations, as I mentioned, are interpretations in which the state of the system is not like a fact of the world necessarily.
Excuse me.
Bless you.
Sorry.
It's not a fact of the world necessarily. It might be a representation of things that have happened in a certain sense, but it's not like a real thing somehow, whatever real means. But and when you're like really taken by this idea, then interpretations where the state of the system is like an objective feature of the world, or like an element of reality or something that's real out there, independent on the observations and stuff like that, are very weird. And on top of that, this story of like, we'll solve this thing by adding many parallel universes in the world, also wasn't a great idea for me. And there were a few things that made me not consider Everettian quantum mechanics very seriously.
So just to clarify, the applying many worlds interpretation, Everettian interpretation to this thought experiment would be saying the friend actually sees 0 and 1. There's these two branches of the multiverse inside this lab where they've physically seen both. And then the explanation is then that when Wigner interacts with friend, Wigner joins in this branching superposition, entangled superposition, and then Wigner and the friend both see 0 in superposition with Wigner and the friend both see 1, and these are both physically real branches.
Yes.
Yeah.
Yes. So in this interpretation of quantum mechanics, what we see as randomness in the world, so this unpredictable quantum phenomena, and we don't know which one is going to happen. In this interpretation, they both happen, right? They both happen, but they happen to different people somehow. So inside the box, when friend does this experiment, there is a friend that sees the outcome 0, and there's another friend that sees the outcome 1. And I thought this was put in by hand, but actually it follows from the mathematics of the theory. We can get that into later. But basically, the mathematics predicts that inside the box now there are two patterns: the pattern of the friend sees outcome 0, and the pattern of the friend sees outcome 1. And these two things become independent really fast, and they don't ever interact again. So the possibilities somehow are both. They both materialize, but they materialize in such a way that they're parallel. That's why they call it parallel universes or whatever. They happen in parallel, and like maybe there is a sense in which they're both inside the same box or not. It's a bit complicated, this, I think, still I'm talking. But yeah, it's exactly as you said. And when Wigner opens the box, then both outcomes will happen to him too. He will see friend having seen 0, and he will see also friend having seen 1, but they will happen in two different realities in a way.
Yeah. And you didn't like this, and was that related to the fact you thought this was kind of put in by hand? Or what was the...
Yeah, I think many people still think that these parallel universes are put in by hand, and I think at the beginning they were, maybe not at the very, very beginning. So I call it Everettian quantum mechanics because Hugh Everett, who was a researcher in his PhD thesis, came up with this idea. But the original, I still have to read the original thesis in detail because there's like a short version, and then there was like the highly edited version, and there's like a longer version. And I mean, in principle, you should study the original text, but also in physics, what matters is the current ideas.
Yeah.
But sometimes we give names to the first people that came up with the idea, so we call it Everettian quantum mechanics. But most people call it many words. And this gives the impression that, you start with the idea that there are many words, that there are many parallel words. Either always existed, like they're really like running in parallel until something quantum happens and then they split, but they were already zillions of them at the beginning running in parallel, or they get created at quantum events, like this measurement here. But actually there is a more refined way of looking at the theory, which is I think it is actually relatively modern in the sense that for a long time people did want to have they had to put these universes in the theory by hand. But in the modern versions of the modern understanding of Everettian quantum mechanics, you can see the universes as emergent patterns in the evolution of the quantum state of the universe. And so somehow the quantum mechanics, so in this point of view, the state of the universe is like the complete description of what's going on. It's in a way you could say it's the word, or a representation of the word, this mathematical object. I mean, this is just a really simple thing, but in principle you could have a very complicated quantum state that tells everything that's going on in the universe. And that's the complete description. And quantum mechanics allows you to compute how this thing changes in time, say for example. And in the evolution of this state, which is also a really complicated thing, but you can probe it mathematically by looking at it in different ways. In this awesomely complicated evolution, there are some patterns that you can see. In particular, if you were to model this thing, you will soon notice that the evolution of the state splits into two patterns. One pattern that, taken on its own, is a description of a friend seeing the result 0, and another pattern that is the description of the friend seeing 1. And these two things kind of exist in parallel in the mathematics. And then you're like, okay, if there is a pattern in my theory, then that's kind of a way of saying something is real in my theory. But it emerges the same way that, water, the wetness of water is something that emerges from the actual movement of all the complicated molecules, the complicated movement of all the molecules in the glass and the interaction between those molecules and whatever touches it. That's a high-level description of what's going on. At a lower-level description is just atoms flying around and bumping into each other. Same way here, like at a low-level description, there is just a quantum state doing its own thing. But if you kind of, squint and you kind of don't check the fine-grained details of the thing, then you start seeing these larger patterns. And these patterns are the words of the many words interpretation.
Yeah, that's a nice way of putting it. It's, emphasizing that it's emergent. So, is there anything that you find problematic at the moment about this Everettian interpretation that's kind of bothering you?
Yes. Firstly, this picture of constantly emerging new realities is a bit unsettling, right? It's it's not just when something like this contrived happens. It's not just when an experimenter makes an experiment and there's suddenly two branches of the word. It's any effect of quantum randomness leads when it's like amplified to our level, to the level where we have solid objects. Whenever some microscopic quantum event can affect something big, it will affect it, and it will affect it in all the possible ways that it can affect it, and that means that there's going to be all these new realities. So one thing that people like to say is that because the weather, the butterfly effect, the weather of our Earth depends on tiny microscopic fluctuations of the pressure and the temperature and so on. And these differences get amplified. That's when they say that the butterfly flapping the wings or not can change whether there is a tornado or not in the world somewhere. This is true also for microscopic fluctuations in the pressure. And so these things at the level, you have quantum uncertainty in what the air is doing, and that uncertainty gets amplified. And then in different universes, we have different weather. So, and there's all these things, and it's funky and it's fun in a way to think about it. But if you spend a lot of time thinking about it, it's unsettling in a certain way. And here is where we're coming full circle with QBism. Like the main problem with this is actually how to understand how we use probability and how we see randomness in in a world where everything happens. Like normally we think about probability as about different things happening, different things possibly happening, but only one happening. And the probability is kind of our uncertainty of which one is going to happen. And one way to look at it is, I don't know in which branch, I don't know which event I will end up seeing. I know there's going to be a different version of me that sees the other event. And that's, in a way, it's fine. Like I think all the probabilities, I don't know which one. But the thing is, whenever we do an experiment of this form, where there's just a few outcomes, we know for certain that there's going to be a version of us that sees each possible outcome. And so it's a bit complicated to actually understand what we mean by saying that there's a different probability for one or the other. So here it was 50-50, but say that it was like 90% 0 and 10% 1. Still both outcomes will happen. So what does it mean for me? What does it mean for there to be a 90% chance? And I mean, this is a very simple way of putting it, and we have some sort of explanation on how to get something like probabilities out in the theory. Or not, I mean, probabilities, you can find them in the theory, that's not too difficult. The question is, what do they mean? Yeah. And this is done, in the approaches is done very similar to the approach of QBism, where we were saying that probabilities somehow are like they're like a codification of our beliefs and also a guide to make decisions. Somehow also in this Everettian multiverse, people embedded in the multiverse somehow can use the probabilities of quantum mechanics to guide their decisions. And there's several people who have worked on this. There are several papers, books even about it. But still, I think it's the main problem. Like there are ways to get out of it, but I think it's still very counterintuitive. It hasn't really solved the problem, I would say.
Right, interesting.
Yeah.
So we've been through this journey of confusion about the double slit experiment to QBism, to relational quantum mechanics, to Everettian. And now, how do you see both, I guess, your view on this and the field as a whole evolving from now into the future in terms of interpretations of quantum theory and possibly solving these problems or converging to some interpretation?
Right. So it's a great question. I feel like one has a tendency often to sort of try to figure out which one is the best interpretation, and kind of then once they figure it out for themselves, they pick that, and then they defend that, tooth and claw in conversation and in papers. And there's a lot of energy spent kind of convincing everybody else that their interpretation is wrong somehow.
Yeah.
And we were talking about it here at the conference. It's not clear whether it's useful to think that one interpretation is right and the other ones must be wrong, and then somehow there is the best interpretation. Somehow, I mean, it's something that we can believe, of course, that there might be a correct interpretation of quantum mechanics, but while we are not there yet, it could be just useful to try to see all the possible coherent ways of thinking about quantum mechanics and kind of exploring them systematically, in a sense. If one's aim is to find the best one or find different good ones to think about. Another approach is to just, which I guess it's been kind of my experience, it's kind of pick one, roll with it for a while, see how you feel, see how how you feel, but see how it helps you with your other questions in physics, right? And see if it clarifies certain aspects of things, and kind of try to collect as much understanding of as many as you can to see what's going on. And I feel like perhaps the field is moving a bit in this direction. I feel some people are more like actively holding this position of like trying to figure out what are all the possible ways and trying to understand how they differ from each other. And that's kind of exciting. And there are results like Bell's theorem. Now it's 60 years anniversary of Bell's theorem. Or like extended, also called extended Lagrange scenario. There are this kind of which involves this, but also another copy of this setup, and they're entangled with each other. It's a bit of a complicated story. But there are things like this that allow us to to somehow think of all the possible ways that we could think about quantum mechanics and rule out ways that are inconsistent somehow. And this is a fascinating research project that is kind of, you can actually go and do some experiments even. Like, oh, this kind of experiment tells me that I cannot think that the world behaves a certain way. Like, it's just ruled out all the possible theories that have this feature. Say like, well, whatever, let's not get into it, but like, it just tells you certain theories just do not work. And other theories can still work. And it's a very interesting research project.
Yeah. Yeah, cool. So there's promising avenues for research on these problems and actually making progress on understanding these theories better.
Yes. And I think perhaps it's probably also good not to only work on interpretation of quantum mechanics. It's good to actually go out and do some physics as well with your favorite interpretation in mind to see if it helps.
Yeah.
Because if maybe it's very nice for some reason that you like some sort of philosophical aspect of it. I don't know, some people don't like randomness, some people don't like faster than light connection between particles, some people don't like the universe being multiversal or these things. And that might make you pick one interpretation over another. But then on top of that, there is also like, is the interpretation giving you a good way of thinking about physics? Like, does it help you be less confused when you do your own computations?
Yeah, that's a good point. And in terms of your own research, are you doing work related to these topics, or with that in mind that you're doing now or planning to do?
Right. So I've been working on foundations, on interpretations, and also on just more like standard quantum field theory stuff. Well, not exactly standard, it was like the gravitational field of very light quantum objects. Well, very heavy from quantum perspective, very light from the gravity perspective. And that involves field theory, and in that sense, it actually helps to think that there is something in your experiment, and it's not just, oh, I'm predicting what's going to happen to me if I predict the experiment. It's good to have some sort of model of something that's happening. That's very useful. And also, I guess when I was studying this extended Wigner scenario that I just mentioned before, and trying to understand how it rules out different kind of explanations, and there actually it was better not really to think about any interpretation and just think about all the possible interpretations, or even just take a step back and don't even think about quantum mechanics. In a way, it's helpful. So yeah, it's a bit of a mix.
Yeah, that's interesting. That it's useful to kind of take a different broad position for different projects depending on what your goal is.
Right, yeah. Like for sure, if you want to work with like quantum computers, sometimes it's easier to just think about the state as a mathematical thing that predicts the future, nothing else. There's no point in trying to think, oh, what are the parts of the computer doing? And sometimes they're actually useful, so it really matters to switch from one to the other.
Yeah, cool. So, I think we've covered a lot of ground, so I'll try and just summarize what I've understood from this conversation. So, the double slit experiment poses us with this weirdness of quantum mechanics, of what's actually happening to this photon that seems to interfere with itself and go through both slits somehow. And then the QBist interpretation of quantum mechanics is based on this idea of the observer being central to what quantum mechanics is telling us, and it's telling each of us as an observer what the probabilities are of different outcomes of a quantum experiment. And that's what quantum mechanics tells us about the world, is how to modify our understanding of those predictions from what it was before. And then, so some people might find that not so satisfying because of the centralness of the observer as one aspect. And then the relational quantum mechanics kind of removes the observer as being special, and it's more about taking different subsystems and considering the relations between them, and then that defines what quantum mechanics is telling you is to do with what your relation is with something that you've interacted with, and it's about the relations between systems that have interacted. And there's some problems with understanding, for example, what's happening in a Wigner's friend experiment where we have an observer in superposition and you're trying to understand the relation between the experiences of observers that haven't interacted. How can we understand the reality of their perspectives in a kind of global universe? And then there's the Everett interpretation, which says that what's actually happening is that both these, when you're in a superposition of having measured 0 and 1, there's actually two versions of you, and these are all kind of physically real branches happening. And then that has the question of what probabilities mean in this context where everything is happening. And there are various approaches to that, but they've not got a consensus, and they all have problems that different people find not satisfying. And there's also the strangeness of having this very, very huge number of different worlds all happening at the same time due to microscopic quantum effects having macroscopic influence. And shifting between different points of view of your kind of understanding of what's actually happening can be useful depending on what problem you're actually trying to solve in a physics context.
Yeah, that's right.
Mm-hmm. Cool. So is there any kind of final words that you'd like to share with our audience?
Yeah, sure. So since we've been talking about doing research, I feel like one of the biggest shifts from going from being a student, bachelor's and master's, to start doing research as a PhD student, is that all of a sudden all of a sudden physics is not something that's written in a textbook that is clear and defined and there's all these rules and things. All of a sudden physics is like this huge mass of confusion, and you really it really changes your perception of what science is. Like you realize that all the nice little theorems and laws in your books were the result of an enormous amount of confusion and discussion and debate that took months, years, decades, centuries sometimes to like settle on the form of our equations and the ways we think. And I think this is particularly strong in foundations of quantum mechanics, where now this discussion has been on for almost 100 years. Heisenberg wrote quantum mechanics like in the first complete form of quantum mechanics, say in 1925, together with Born and now a blank. But anyway, and we are still debating on what are the useful ways of thinking about this theory. And it's a privilege to take part in this conversation over centuries, and but it's also it's confusing doing the step from PhD, like from master to PhD. You suddenly realize this, and it's true for many fields, because this other stuff I was doing with gravity, it's a much less confusing in a way, like at least famously, like less confusing than interpretation of quantum mechanics. But still, the agreement that we reached over the 3-5 years where I was very active in this field was the result of a lot of debates and confusion and arguments and beers and emails and stuff like that, papers, wrong papers, right papers. It's really fantastic mass, and it's not clear from the outside often that science works like that.
Yeah, that's a very good point, that we're living through the confusion of this part of physics, but that also existed for all these other parts of physics that we take for granted.
Right, yeah. Now. And you don't see it anymore because you got the product of this thing.
Yeah, cool. Yeah, nice comment. Cool, so I think we can wrap up there. So thank you, Andrea, for joining us for this episode, and thank you for joining us as well and making it to the end of this podcast. And please join in next time for more Quantum Foundations discussions. Leave any comments in the comments. Happy to have a look, or questions. And look forward to seeing you next time. Bye.
Bye. Wait, I'm too tall.
Smiling.
Is there a way to untall myself? Okay.
Yeah.
Are my glasses? Oh, no.
We do like cheers.
Cheers with water. It's a bit silly now. It's a bit silly. It's vodka. We're gonna have something cool.
Yeah.
We'll write this down.
Okay.
Ready?
Yeah.
Do I need to look at the camera? Maybe.
No. Well, you can. Yeah.